Hello, this is Dr. Jenkins again, and here we are for our video on Chapter 2. This is going to be a bit of a review on chemistry. We're not going to go that in detail, but before we continue to move forward and talk about body systems, it's really important that we remind ourselves of some really important chemical stuff, because it's going to come back to us later. Hopefully you've had chemistry before. So it tends to be, for a lot of people, this is a more simple review. But for other people, if you haven't had chemistry or haven't had it in a while, you may need to spend more time with this. So wherever you are in that, make sure that you understand this material. Don't feel bad. Some people haven't had a lot of chemistry, so this can be new and it can be very challenging. So don't feel bad, but just recognize where you are and then spend the time that you need to understand the material. And as always, I am here if you have questions. And, why is it important? Well, before we can play ice hockey, we must be able to skate first. So we're just laying a foundation. And as I said, once we get to the nervous system, I'm going to be talking about potassium and sodium ions. We're going to talk a lot about water. And it's really important that we understand some of the chemical properties of them, because that's really important to understanding how things work. Okay. So we're going to be going over some basic chemical definitions. We're starting small. So atoms are our smaller chemical pieces, and then we're going to work our way into bigger and bigger. Let's do it. So atoms are the smallest chemical particles that we have in our body. You can really keep it that simple. Atoms are smallest chemical particles. When two or more atoms join together, they form a molecule. So that's what I've shown you here. Here we may have the hydrogen atom, right? It's a small chemical particle. When we join two atoms together, it forms a molecule. H2O is an example of a molecule. It is one oxygen and two hydrogen atoms. Then we have these things called elements, and this can be a little tricky. There's something about an element that makes it unique. So it's a unique thing made up of atoms. And we can pretty much keep it that simple. You may recall the periodic table of elements, where we have oxygen and hydrogen and neon and argon, all those things. Excuse me. So an element is a unique substance made up of atoms. And then, of course, matter is the biggest thing of all. Matter is anything that takes up space and has mass. So it could be a gas, like oxygen gas. It could be a liquid, like water. Or it could be a solid, like a bone. So basically, we combine atoms to form molecules, and then we have bigger conglomerations called matter. So here we go. Atoms, as we already said, are the smallest particles. Here's an example of a hydrogen atom. For example, here's an example of lithium, not one that we'll talk about in the body, really. Make sure you review the basic structure of an atom. Atoms are made up of protons, neutrons, and electrons. Let's look at lithium because it gives us a better example. We have a nucleus. I think most of us are familiar with a nucleus. It's a central part. So inside the nucleus, or this central part, we have protons and neutrons. Protons, as the name suggests, has a positive charge. Neutrons have no charge. They're neutral, as the name suggests. So in the case of lithium, for example, inside we can see 1, 2, 3 protons, and then right behind it we see 1, 2, 3, 4 neutrons. Now, we have the nucleus, but then we also have these outer electron shells. So these are the outer electron shells. And these are the only two parts of an atom. The only two parts of an atom, you have the nucleus and you have electron shells. The nucleus contains the protons and neutrons, but it is the electron shells that contain the electrons. There's an electron, there's an electron, there's an electron. And it kind of makes sense, folks. The electron shells house the electrons. Well, I'll be. And the electrons have a negative charge. Excuse me. So you should know all of this. We have two main parts of an atom, the nucleus, which contains protons and neutrons, and the electron shells, which exist outside of the nucleus. And the electron shells contain electrons, which have a negative charge. Seriously, folks, if you need to take time with this, do it. I know it can be a little intimidating if it's new or kind of new. This is saying the same thing. We already know that the protons are in the nucleus. They have a positive charge. Neutrons are also in the nucleus. They have no charge. And the electrons in the electron shells have a negative charge. Okay, more about the electron shells. Let's build one. So we're going to have our nucleus, and that's going to contain protons and neutrons. And then we have these outer electron shells. There can be a few or many, so sometimes there's only one electron shell. Other times there's 10, so it just depends. Okay, the first electron shell, the one that's closest to the nucleus, this can only hold 2 electrons. It can hold a maximum of 2. That is it. Sometimes there'll be 1. If we look at hydrogen, it only has 1 electron. If we look at helium, it has 2 electrons. But what if we have more than 2 electrons? Well, because the first electron shell can only hold a maximum of 2 electrons, if we have a third electron, we have to make another electron shell. So in the case of lithium, we fill the first electron shell, 1, 2, and then we make an additional electron shell for the third one. So the first or closest electron shell can only hold a maximum of 2 electrons. Now, the remaining, whether it's the second electron shell, whether it's the third electron shell, whether it's the 10th electron shell, each additional electron shell can hold a maximum of 8. Sometimes you only need 1. Sometimes you need 2, 3, 4, 5, 6, 7, 8. Each additional electron shell can hold a maximum of 8. It's called the octet rule, because 8 octo. If we have an additional electron, and we filled the first shell with 2, we filled the second shell with 8, then we've got to move on to a third electron shell. And it continues from there. By the way, that closest electron shell, oh, hold on. Let me rephrase that. The outer electron shell, whatever it is, whether it's the first one, because there's only one, or whether it's the third one, like in a chloride ion, The outer electron, the outermost electron shell, is called the valence shell. Again, you may be wondering, why are we going over this? Well, because a lot of the stuff we're going to have to come back to later in the course. Because it matters. Okay. All right. Let's talk about some other stuff. Atoms are most stable when the outer electron shell or valence shell is full. This is really important. Atoms are most stable when the outer electron shell is full. And when we say most stable, we mean that it's least likely to be in a chemical reaction, because an unstable atom is more likely to chemically react. But a stable atom will not react very easily. So look at our examples. Look at hydrogen. Hydrogen has only one electron in its valence shell. And this particular valence shell, because it's the first, can only hold a maximum of 2. So therefore, the outer shell is not full. And we can consider this atom to be more unstable. Which isn't necessarily a bad thing, because we like hydrogen to be unstable, because then it will participate in chemical reactions. Think of an easy example, water. We like the fact that it's unstable, because it can easily join up with oxygen to form water. On the other hand, let's take the chloride ion. Its outermost electron shell, or valence shell, has 1, 2, 3, 4, 5, 6, 7, 8. Wait a minute, it's full, right? The first electron shell can hold a max of 2, but every additional one can hold a max of 8. So in this one, the outermost or valence electron shell has 8. It's full. Therefore, this is more stable, not likely to participate in chemical reactions. You know, maybe you're listening along and you've never understood chemistry before, but now you're like, oh my God, it makes sense. Haha, that's my goal. Okay, now if we look at a generic atom, this isn't always true, but for understanding's sake, let's just look at a generic everyday atom. A generic everyday atom, not always, but in many cases, a generic everyday atom is overall neutral. Look at helium. Helium has 2 protons. 1, 2. Protons have a positive charge. It has 2 neutrons, which have no charge. And it has 2 electrons with a negative charge. So here we have 2 things with a positive charge, 2 things with no charge, and 2 things with a negative charge. If we have 2 things that are positive and 2 things that are negative, well then the result is neutral. That's why we can just write helium like this. It doesn't have a positive or a negative, because overall it's neutral. It's got 2 protons and 2 electrons. They balance each other out. Okay. If you need to, take a minute, review, pause, come back later. Whenever you're ready, come on back. Now, we already talked about a molecule is when 2 or more atoms join together. This happens all the time, right? We constantly have atoms forming together to make things. It's great. So let's give an example. Here we have sodium, and here we have chlorine. Let's look at the makeup of sodium. In particular, I want to look at the electrons. Now, don't worry, because I'm not going to be giving you pictures of atoms on our exams. It's more about understanding the concept, okay? Sodium has 11 electrons. We fill the first shell, 1, 2. Then we continue on to the second electron shell, 3, 4, 5, 6, 7, 8, 9, 10. We've filled the second shell with 8. And because we have 11 electrons, we need to make one more to make 11. On the other hand, we have chlorine. Chlorine has 17 electrons. We fill the first rim, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Cool. Well, now, remember, atoms are happiest or most stable. Atoms are happiest or most stable when their valence shell is full. So in this case, sodium and chlorine, they are like a match made in heaven, like peanut butter and jelly, peas and carrots, chocolate and peanut butter, because sodium has 11 electrons. Its outermost valence shell has only 1. It is unstable. Chlorine has 17 electrons. Its valence shell has 1, 2, 3, 4, 5, 6, 7. It is almost full. Well, if we form a molecule, check it out. We just take 1 electron from sodium and we give it to chlorine. Now, once we give this one away, the outer shell of sodium is now full. 1, 2, 3, 4, 5, 6, 7, 8. We did have another one, but we just gave it away. So now the valence shell is full, sodium is happy. Chlorine initially has 7 electrons in its valence shell. It only needs 1 more to be full and happy and stable. Well, upon receiving that electron from sodium, now the valence shell of chlorine, it already had 7, but now it has 1 more. So now its valence shell is full. So now both valence shells are full, both atoms are happy, and we have the sodium chloride molecule where 2 atoms join together. And we're going to see this pattern. Atoms like to combine when they can make their valence shell full. Okay, we're going to come back to that. You know, I mentioned the elements, that they are unique substances made up of atoms. Here's the periodic table. You do not need to know this periodic table. And hope that's okay with you, because it's okay with me. All right. When we talk about elements, you know what's really cool? In our body, we have a lot of elements. We've got sodium, potassium, calcium, iodine, iron. We got plenty of elements in our body. But you know what? Over 90% of all the elements in our body are the same 4 elements. So even though we have other elements, and these other elements are really important, calcium, potassium, sodium, iron, these are really important, but we don't need that much of them because 90% of the elements in our body are these 4: carbon, hydrogen, oxygen, nitrogen. Make sure you know those. I put them in this order because it makes a nice little CHON, cone. That's how I remember it. Carbon, hydrogen, oxygen, nitrogen. That's really cool. We have other important elements, but by quantity, over 90% of our body is made up of only 4 elements. You should know those 4. Okay. Sometimes we have a little bit of a variation of an atom or an element. And one example is an isotope. An isotope is an atom that doesn't have the same number of protons, electrons, and neutrons. I already gave you an example okay, let's give an example. We have the nucleus And then we have the electron shells. Usually, we have the same number of protons, neutrons, and electrons. Let's say we have 3 protons. Let's say we have 3 neutrons. And then we would have 1, 2 to fill up the first electron shell, and 3. So usually we have the same of all. 3 protons, 3 neutrons of no charge, and 3 electrons with a negative charge. So in this scenario, there's no overall charge. The overall atom is neutral. But sometimes there's a variation. And one example of this is called an isotope, where now we have a different number of neutrons. So an isotope of this atom, instead of having 3 neutrons, maybe it has 5. It doesn't change the overall charge, but it just means that the number of neutrons is not the same as the number of protons and electrons. It's a slight variation called an isotope. Why do we care about isotopes? This is an example of a carbon isotope. I'm not going to ask you those specifics. But why do we care about isotopes? Because we use them practically. Isotopes can be used with imaging. I'm not going to ask you this specifically, but I'm just trying to give you an example of why we care about this variation. Chemically, when we change the number of neutrons, it changes the atom. And sometimes we can use that to our benefit. This is called a PET scan, where they inject dye into the bloodstream, and then they take a picture. This is a brain at the bottom. This is a thyroid gland at the top. Well, the dye that they inject contains an isotope of iodine, and that isotope just so happens, because of that chemical variation, to react with the imaging machine to allow the dye to change colors. We can also use isotopes in radiation therapy to kill cancer cells. Now, these happen to be what we call radioactive isotopes. They're definitely a little sparky, but that can be a good thing for someone who's suffering from cancer. All right, already talked about matter, anything that takes up space and has mass, 3 forms of matter, solid, liquid, gas. There's examples of all 3 of these in our body. In our body, we have oxygen. We have carbon dioxide gases. We have liquids. And we have a bunch of solids, bones, muscles, liver tissue, all that. Here are some examples. Okay. Little humor to start things off, or to continue things off. Okay. Let's continue. All right, so obviously, things in our body don't exist alone. We have an atom over here, and we have an atom over here. In many instances, they form something together. So in our body, a lot of things join together. And there's different ways that we can join things together in our body. Now, don't overthink this, ladies and gentlemen. We can combine something physically, just throwing them together, or they can be combined and they can form chemical bonds. So sometimes you just join things together and they exist together, but there's no chemical bond as a physical connection. Other times we put 2 things together and they chemically bond. Okay, let's look at physical combinations. When we just throw things together and it's a physical combination. They exist in the same space, but there's no chemical reaction. We have some examples of physical combinations: a solution and a colloid and a suspension. Okay, bear with me. A solution. So you see an IV bag, right? An IV bag is a solution. What are the two things present in an IV bag? Water and salt. That's it, folks. Water and salt. To make this IV bag, that is way overpriced from the medical supply companies, to make this IV bag, we simply put a little bit of salt into water. What's happening under the surface, they just exist together. There is no chemical reaction. Water is not altered. Salt is not altered. Another example of a solution would be Kool-Aid. If you have a Kool-Aid container, what are the two parts? Water and the sugar packets. Well, let me get blue here because I can do that. We have water, and then mixed in with it, we have these sugar molecules. Even though the sugar dissolves in the water, there is no chemical reaction. Dissolves just means that the sugar molecules spread out nice and evenly. But there's no chemical reaction. It's a solution. Make sure that you know these definitions. I'll use blue. Solute and solvent. In a solution, whatever is present in smaller amounts is said to be the solute. In our examples, in an IV bag, there's much more water than salt. So because there's less salt, salt is the solute. In Kool-Aid, even if you add a lot of sugar, which some people do, there is still always going to be more water. So what's present in smallest amounts? Sugar. Sugar is the solute. On the other hand, whatever is present in larger amounts is the solvent. Water and water. Most often in our body, the solvent is water. It is what's present in largest amounts. It is also what things dissolve into, but the more technical definition is it is what's present in largest amounts. Excuse me. Now, a true solution is homogeneous, which means that it is the same mixture throughout. If I looked at this IV bag, if I took a sample of fluid from here, if I took a sample of fluid from down here, if I took a sample of fluid from over here, every spot would have the same concentration or makeup. It's a homogeneous mixture. It's the same concentration throughout. In other examples, it is not homogeneous. An example of a heterogeneous mixture would be, what if I put sand in water? It's a physical combination because I'm literally just throwing the sand into the water. There's no chemical reaction. But it wouldn't take very long if I let it set out for the sand to settle to the bottom. Well, the fact that the whole solution isn't the same, up towards the top it's more water, less salt, then at the bottom it's more salt or more sand, that would be a heterogeneous mixture because the contents will settle. These are examples of a physical solution. I already gave you Kool-Aid. Gatorade is another example. I've already introduced this, but now I'm just giving you a slide. There can also be a physical combination where the contents settle. I gave you the example of sand and water, but blood is also an example. Now, sure, at first, if you look at blood, or if you shake up this test tube, the blood cells will be distributed evenly through the plasma, and it would be homogeneous. But if you let it sit for a period of time, the blood cells would sink to the bottom. So it's still a physical mixture, but the contents would settle, and therefore it's not homogeneous. Examples of heterogeneous physical combinations would be what we call colloids and suspensions. You don't need to know the difference between the two. All right. Now we can also mix things through chemical bonds. We just covered physical bonds. Well, we can also combine things through chemical reactions. And we're going to cover 3: ionic, covalent, and hydrogen. Don't be scared. In an ionic chemical bond, electrons, this should be electrons. I apologize for that. Electrons are transferred or given from one atom to another. And what's cool is that I already gave you this example. Remember? We talked about the sodium atom having 8, 9, 10, 11 electrons. So in its outer valence shell, it only has 1. Versus chlorine that had 17 electrons. So its outer valence shell had 7. This is a match made in heaven. So sodium gives 1 electron to the chlorine. And now, sodium has 10 electrons, and the chlorine atom has 18. But their valence shells are full, and they are happy. So this is an ionic chemical bond, where electrons are transferred. One atom gives to another. The example is sodium chloride. Any type of ionic bond results in something called ions. Hence the word ionic chemical bond. An ion is a charged particle, period. Now, you might have water. You might have oxygen gas. You might have CO2. You might have iron, iodine. We have a whole sort of thing. Hydrogen, hydrogen usually is an ion. I take that back. So we can have a bunch of atoms and molecules that are neutral. These are all neutral because there's no charge written beside them. But then we can have ions. And look down here, Na plus, Cl minus. So when we have a plus, potassium, calcium, chlorine, when you have either a plus or minus after it, it is called an ion, charged particle. And we know already how it gets charged. We can look to the bottom for these examples. How many electrons does sodium have? 8, 9, 10, 11 electrons, and it has 11 protons. Chlorine has 17 electrons and 17 protons to begin with. But what did we do? Sodium gave an electron to chlorine. So now we still have 11 protons. We still have 17 protons. But now sodium, because it gave away an electron, now only has 10 electrons. On the other hand, the chlorine atom had 17 electrons, but now it gained 1. So now it has 18 electrons. If you look at sodium, it has 11 positive things and 10 negative things. So it has 1 more positive than negative. So the resulting ion is a positive charge. It has 11 positive things and only 10 negative things. So the overall charge is positive. Chlorine has 17 positive, but 18 negative. So now, and that should be electrons, my bad. So because there's one more negative, it becomes Cl minus. So sodium plus, Cl minus are examples of ions, charged particles. And they got that way as the result of an ionic bond, where an electron was given or taken away. This is pointing out just the same thing I said before. Anytime you see a positive or negative, it is an ion. Okay. Now, in an ionic bond, we give or take away an electron. In a covalent bond, electrons are shared. We don't give or take away, they are shared. And that's why I have the picture of two people shaking hands. Let's look at oxygen gas, which is O2. Initially, oxygen has 8 protons and 8 electrons. We have 2 in the first shell and then 6 in the next. So this is also oxygen, so it's got 8 protons and 8 electrons. In the outer valence shell, there's 1, 2, 3, 4, 5, 6. Well, how many? Remember, atoms are most happy when their valence shell is full. It has 6. How many more does it need to get to 8? 2. So in a covalent bond, 2 pairs of electrons are shared. This is now the oxygen molecule. So now, if we compare and count, the outer valence shell of each has 1 electron, 2, 3, 4, 5, 6, 7, 8. It's full, it's happy. The other oxygen gas can also count these middle 4, 5, 6, 7, 8. Okay, so the electrons are shared. It does not result in a charged particle. Okay, here are other examples. Sometimes only 1 pair of electrons are shared, sometimes 2 pair, sometimes 3 pair. You don't need to know examples of this, just know that it is considered to be a covalent bond when electrons are shared. Alrighty. The last type of chemical bond we're going to discuss is something called a hydrogen bond. Take a sip of water here. A hydrogen bond is a weak covalent bond that involves hydrogen. I should say hydrogen. A hydrogen chemical bond is a weak covalent bond that includes hydrogen. After all, folks, that's why we call it a hydrogen bond. So it's a weak covalent bond that includes or involves hydrogen. Water molecules are attracted to each other by hydrogen bonds. Now, these bonds are weak, so weak that the water molecules aren't even touching. In a covalent or in an ionic bond, the molecules are touching, but not here. There's one water molecule and then another and then another. They're close, and it is that attraction between them that is considered a hydrogen bond, a weak covalent bond. Now, there really aren't lines in between, but those lines are there because it's meant to identify an attractive force. It's kind of like when you get 2 magnets close together. Well, a magnet close to something that it can stick to. They may not be touching yet, but there's an attraction between them. We like this. Do you know why? Because it allows water molecules to cling together. So it keeps the water molecules close. We like water molecules to be close to each other, so water can flow together. This allows water to easily take part in chemical reactions. We can easily just take one out. So this water molecule at the top might leave and go take part in a chemical reaction. But then it could easily just come right back. This is possible because of the weak nature of the bonds. If they were ionically, or more specifically covalently bonded, it would be harder to pry one water molecule away. So weak isn't always a bad thing. These hydrogen bonds, or the attraction between water molecules, is also good because it allows things to easily dissolve. If I want to dissolve anything in it, sodium, to make saline solution, sodium can just dissolve right in the spaces. We like that. So these are all chemical properties of what makes water so valuable in our body. And water is so valuable in our body in large part because of these hydrogen bonds, or weak covalent bonds. All right, good stuff. Okay, so the second part of this chapter, I'm going to continue in another video. So watch this one, take a break, or if you're ready to go to, just sign on for the next video.